All right, here we go. This is Unit 6 in Algebra 2. The unit is called Exponential and Logarithmic Functions, Equations, and Expressions. And this is Lesson 1. Lesson 1 is called Exponential Growth and Decay, Word Problems. So its first definition is exponential functions. Exponential functions look somewhat familiar to functions that you've seen before in that they involve exponents, but there is a big difference in that the variable is now the power rather than the base. Okay, so previously in this class we've dealt a lot with functions such as f of x equals x squared, where the variable x was in the base. Now the variable x is going to be the exponent. So for example, g of x equals 2 to the x power. Okay, the base is the fixed number and the power is the variable. So this is an exponential function. F of x equals b to the x power. B is the base, and the exponent x is the exponent. And it says here b is greater than 0, and b is not equal to 1, because if b is equal to 1, then you have 1 to a power, which just equals 1. So b does not equal 1 in this case. If the original amount is increased by a consistent rate over a period of time, then it is known as exponential growth. Which usually looks like this when you graph it. If the original amount is reduced by a consistent rate over a period of time, then it is known as exponential decay. And then the graph usually looks like that. Okay. A function of the form f of x equals a times b to the x power, with a greater than 0 and b greater than 1, is an exponential growth function when it increases as x increases. Okay? So when b is greater than 1, it's exponential growth, because when you raise a number greater than 1 to a power, it gets bigger. When 0 is less than b, which is less than 1. So when b is between 0 and 1, it is known as exponential decay, because if you raise a number between 0 and 1 to a power, it gets smaller. Okay? Think about like 1/2, for example. 1/2 to the second power is 1/4. 1/2 to the third power is 1/8. 1/2 to the fourth power is 1/16. So it's getting smaller. Okay? So when b is greater than 1, it's exponential growth. When b is between 0 and 1, it's exponential decay. Example 1, determine whether each function represents exponential growth or exponential decay, then find the y-intercept and identify the parent function of the given function. Okay? So first of all, for example 1a, you're looking at the number that's being raised to the x power, which is just the 5. Okay? Since 5 is greater than 1, it means this is exponential growth. Now let's find the y-intercept, because the question says find the y-intercept. Remember, the x value for any y-intercept is always 0, so we're going to replace the x with 0. Anything to the 0 power always equals 1. Okay, anything to the 0 power always equals 1. So this is equal to 4 times 1, which is 4. So the y-intercept in this case equals 0, 4. And then it says identify the parent function. So the parent function, in Unit 2, we graphed 2 to the x power. That's all we did. The parent function for this is f of x equals 5 to the x power. Okay, whatever this is, to the x power. Let's do another one. Okay, for example, so again, for example 1a, it was exponential growth because the number being raised to the x power was greater than 1. In this example, the number being raised to the x power is a half. So since it's between 0 and 1, that is called exponential decay. It doesn't matter that the 16 is bigger than 1. That does not matter. The number that matters is the number in the parentheses being raised to the x power. Since that's less than 1, or between 0 and 1, I should say, it's exponential decay. Next, we're asked to find the y-intercept. Replace the x with 0. (16) times 1/2 to the 0 power. Anything to the 0 power always equals 1. So this y-intercept is going to be 16. It's not always that number. For example, if I do like plus 10 at the end, it won't be the number out front. Okay, just keep that in mind. So in this case, the y-intercept equals 0, 16. And the parent function will be f of x equals 1/2 to the x power. You can model growth or decay by a constant percent increase or decrease with the following formula. Okay? The final amount, which is represented by a of t, equals the initial amount, represented by the small a, times 1 plus or minus r, depending on if it's increasing or decreasing, to the t power, where t represents the number of time periods. Okay? So we're going to use this formula for the next 2 examples. Okay. Example 2. So I'm going to do example 2 and example 3 based off of that example that we just learned about. Based off of that formula I just showed you, I mean. Jim purchased a new truck for $33,000. The vehicle depreciates at 8% each year. That means the value of it is going down. What is the value of the truck after 5 years? Okay. So here's my formula. I'm going to do a of t equals the initial amount of 33,000 times 1 minus 8%, but you have to turn the 8% to a decimal. So to turn 8 to a decimal, okay, I don't know if you just do 8 divided by 100, and it gives you the decimal is 0.08. And then to the t power. Now, let's just simplify that a little bit. Let's do a of t equals 33,000 times 0.92 to the t power. If you can go, you don't have to write step 1 if you know 92%. You can go right to that. Because think about it. If it's depreciating 8% per year, that means it's losing 8% of value per year. In other words, it's keeping 92% of its value each year. Okay? And the question is, what is the value of the truck after 5 years? Okay? Since it's depreciating per year, that means we're going to have 5 periods. Okay, so I'm going to do a of 5 equals 33,000 times 0.92 to the 5th power. So now 0.92 to the 5th power times 33,000. Since it's a money problem and it's asking about value, I'll round to the nearest cent. And I'll say a of 5 is approximately $21,749.69. And since it's a word problem, let's put it in a sentence. Okay, the value of the truck after 5 years is $21,749.69. A motor scooter purchased for $1,000 depreciates at an annual rate of 15%. What is the value of the scooter after 7 years? Okay, so here's going to be my formula. Just another one, just like example 2. The original amount of 1,000 times 1 minus 15%. So 1 minus 0.15 as a decimal to the t power. Again, if you want, you can skip that step. If you know to go to 85% right away, you can. Just make sure you put it as a decimal, 0.85 to the t power. After 7 years, so once per year it says, so we're going to do a of 7 equals 1,000 times 0.85 to the 7th power. Now you're going to do 0.85 to the 7th power, okay? I'm not sure if you can see this very well, but 0.85. Caret key right there. Okay, that's the caret key right there. So you press that. 7th power equals that big decimal times 1,000. $320.58. And then let's put it in a sentence. The value of the scooter after 7 years is $320.58. Okay. Next, we're going to do compound interest. Compound interest is when you earn interest on your interest. So if you have an investment and it's gaining interest, you don't just gain interest on your original amount, you gain interest on your original amount and any interest earned previously. So here's the formula for that. A of t equals P times 1 plus your rate over the number of periods, n, raised to the n times t power. Okay, so P is your principal or your initial amount. R is your rate, and it's as a decimal. Meaning don't give it as a percentage, turn it to a decimal. N is the number of times it's compounded per year. So what that means is if it's compounded once per year, n equals 1. So if it's compounded annually, that means n equals 1. If it's compounded semi-annually, that means twice per year, so n is 2. If it's compounded let's say if it's compounded quarterly, there's 4 quarters in a year, so n equals 4. If it's compounded monthly, there's 12 months in a year, so n equals 12. If it's compounded weekly, there's 52 weeks in a year, so n is 52. If it's compounded daily, we'll say there's 365 days in a year, so n is 365. And finally, t is going to be representing your time in years. Okay, so Diane invests $7,500 in an account that pays 2.75% interest compounded semi-annually. That means twice per year. So n is going to be 2. Assuming she never makes any withdrawals, how much money will be in her account after 15 years? All right, well, let me just copy down the formula from above. A of t equals your principal times 1 plus the rate divided by n raised to the n times t power. So her principal is $7,500. That's what she's investing. Times 1 plus the rate. It says 2.75, but that's a percentage. So you have to turn that percentage to a decimal by dividing by 100. You have to turn that 2.75% to a decimal, 0.0275. See, because above it says rate as a decimal. So even though there's a decimal point there, that's still a percentage, 2.75%. So you have to divide that by 100 to get it as a decimal. It's divided by n, which is the number of times it's compounded per year. Semi-annually means twice per year. And the exponent is going to be n times t, 2 for n, times 15 because it's 15 years. Okay, so let's clean this up a little bit. Let's take care of the stuff in the parentheses. So let's do 0.0275 divided by 2 plus 1 to clean up the parentheses. And when you do that, you get 1.01375 raised to the 30th power. Okay. And then let's do the number in the parentheses, 1.01375. Let's raise that to the 30th power and then times 7,500. And you get the final answer of 11,000. Let's round it to near a cent because it's a money problem. $11,297.63. Not bad. So I'll say there will be $11,297.63 in Diane's account after 15 years. Not bad. Well, she did start with 7,500, so I don't know. Okay, one more type of problem. Interest compounded continuously. Interest compounded continuously. Okay, so here's our formula for that. It's going to be the following. A of t is going to equal P times E. I'll get to that in a minute. To the R times T power. Okay, where P, again, is your principal, which is also known as your initial amount. R is your rate, and again, it has to be as a decimal, not a percentage. And T is your time in years. Okay? Let's see okay. E is actually a number, kind of like pi. Everybody knows pi, 3.14, and so on. E is another number that goes on forever. Okay? It's named after this guy named Euler. His name is spelled E-U-L-E-R. Was pronounced Euler. Okay? And it's like 2.71, 2.72, I think, when you round it. Okay? So it's just not as popular as pi. There it is. 2.718281828. Okay? So E is a number. And you get that on your calculator by typing seconds, depending what calculator you have. Okay? Mine, I get it by typing seconds and then the LN button. See how it gives me that E right there? I don't know if you can see it well on the screen, but. Okay, so let's do a problem like that. Phil puts $3,000 into an account that earns 1.5% annual interest. The interest is compounded continuously and there are no withdrawals. Shout out to him for that. How much money will be in the account at the end of 10 years? Copy down the formula first. Okay, so the principal is going to be 3,000 because that's what he's investing. E is a number. I'm going to leave that alone. E is a number. R is your rate. Has to be a decimal. So even though 1.5 is a decimal, it's really a percentage, 1.5%. So you have to do 1.5% divided by 100, and you're going to get 0.015 times T. T is the time in years, so times 10. So next step, let's clean up the exponent. Let's do 0.015 times 10, and the exponent is going to be 0.15. Okay, so here's what you're going to do. In your calculator, you have to calculate e to the 0.15 power. So what I'm going to do in mine is I'm going to hit seconds. Now your calculator might be different. I'm going to hit the ln button. And see how that gives me that e? I'm going to type the exponent of 0.15. Equals that, then times 3,000. Gives me the final answer, $3,485.50. Wrote the wrong number. Let me fix that really quick. Okay, so the number should be $3,485.50. And let's put that in a sentence. Did I put the last one in the sentence? Yeah. There will be $3,485.50. In Phil's account after 10 years. Okay. And that's the end of that lesson. That lesson was called Exponential Growth and Decay, Word Problems.